The broadcast is now starting. All attendees are in listen-only mode.
Welcome back to 90.1. We have now the second part to the course. Before we get started, I do want to go over some housekeeping items. Again, if you guys have any question, please feel free to fill out the question, fill out your question, and we will pass that along to either Mac or Joe throughout today's presentation. And also at the end of the presentation, you will see a slide with a link and a passcode. Please use that link and passcode if you have not, to download a PDF copy of today's presentation. And also you will see a link. Use that link and fill out the course evaluation. And once you fill out the course evaluation, you will receive your certificate of attendance with your PDH credits. Without further ado, I do want to pass it over to you, Mac.
Thanks, Brian. So last time, if you remember, we had just completed the economizer section, slide 39 and 40. So we'll start up at 141, and it's really closing out economizer requirement loosely tied to economizers. This is the DX stage requirement for modulating units, and most economizers, most systems, because of our rules, will include an economizer. So it's really for almost all systems except in climate zone 0 and 1. But we require several steps of compressor unloading or multiple compressors, variable speed compressors, so that we can minimize the optimize the unit and minimize the wasted energy of an unloaded big compressor. So basically 3 steps for the smaller units, 4 steps for the bigger units, and units controlled by the space temperature. That means by a thermostat in the room instead of the air supply temperature. Greater than 65,000 shall have 2 steps of mechanical cooling capacity, is the main rule. So anyway, this will match when we go to the fan energy. This will match the fan energy requirements. So we'll step down compressors, we'll step down fans. So when we do economizers, we found that we've required them, and we're expecting a certain amount of energy savings from them, and yet if the controls fail, then we don't get those energy savings. So this follows something that's been in practice for several years in the California code. We require the economizer to have fault detection and diagnosis built in. Now, the manufacturers already offer this because of their offerings in California, so you can get this on normal rooftop units or almost kind of controlled units. So basically, we're going to have a DX air-cooled system. We're going to have sensors that monitor the outside air supply or return air. We're going to display the values of each of those sensors so that we can troubleshoot. We're going to see what the status of free cooling available, and is the economizer actually enabled, and is the compressor enabled, and the heating enabled, mixed air, low limit, cycle active. System can initiate each mode for testing. System reports to the operators, and then it reports the faults: an air sensor fault, economizer mode not matching controls, damper not modulating, excess outside air. So in this way, we can make sure that since we've required this economizer to put in, that the economizer is actually operating the way we want to get our savings. Now, this is for no DDC, and this is the way we've generally set up our VAV boxes. So this is as a VAV box, as a room begins to cool down, the maximum cooling airflow from right to left on the graph there goes from maximum airflow to minimum airflow, and then after a deadband, the heat comes on. In this case, I've showed hot water modulating heat, but it could be electric heat just as easily. And then the airflow stays constant, and the heat increases to meet the room requirements. Now, Always we've had a minimum set point no larger than the larger of, and we always put 30% of peak in. And then we used to have zero point 0.4 CFM per square foot, but we really didn't know where that came from as a committee, so we ended up taking it back out. And then we had a minimum outdoor flow rate required by ASHRAE 62, and then small boxes under 300 CFM, we took the requirement off, but now we've removed that exception, so there is no minimum size to this requirement. Or an approved alternate that the authority having jurisdiction will approve, or if you have other codes such as the healthcare code, the hospital code, or something that requires constant volume boxes or something in that like that, then that's an exception. Now the reheat energy is in that square box. So then if you do have DDC controls, and this started in 2013, you have to use this control sequence. So what happens here is the maximum size airflow set point comes down to the minimum set, goes through a deadband, and then the heat comes on, the first stage of heating, and hits a maximum supply air temperature. If the space is still not satisfied, we allow you to increase the airflow back up to the maximum heating airflow set point, which is generally 50%. So in that sequence, what we allow you to do is use a little less heat, and actually this minimum set point is 20% instead of that 30% we used to require. Deadband does not exceed the larger of 20% of design airflow or ASHRAE 62.1 requirements. Now, so this will save some energy. The air between deadband and full heating or cooling is modulated. So this bringing the air back on helps us in several ways, and it also saves a little energy. So as you're selecting boxes now, you do have to go through a couple of extra steps as you schedule and select. So your maximum cooling airflow CFM would always be normally scheduled on as a VAV box schedule at the top there. And then 20% maximum cooling airflow, or ASHRAE 62, would let you go down to 86 or 184 based on the 20%. But then the 50% maximum cooling flow is would be the part you could speed up to 215 or 270. But then looking at the heating requirements for the box, for these boxes, the minimum heating flow for electric heat would not allow you to go all the way down to 20%. So you have to watch out for that. Also, because of the modulation, the ASHRAE 62 minimum can be played with just a little bit, so there's a little bit of method in it, and you need to work with ASHRAE 62 appendixes to see what I'm talking about there. Now, one of the reasons we did this was a requirement from ASHRAE 62 that requires the supply air temperatures from a VAV box, or being supplied, actually not from a VAV box in their case, but anyway, supplied from overhead, cannot be more than 15 degrees greater than the thermostat set point, if the return is also at the ceiling. So most VAV systems have a return, a ceiling supply and return. So they're saying that this hot air would not fall into the breathing zone, and so you cannot make it any hotter than 15 degrees higher than the thermostat set point. Now, we looked at that. Now, they have some other requirements. They say, and at 4 foot from the ground, the velocity of the air has to be 100 feet per minute. So, and this is a very particular requirement, especially that 100 feet per minute. So what ASHRAE 9.1, we normally would try to write a companion rule that would meet ASHRAE to, but we decided in this case we couldn't. We thought the buoyancy of the air was a good point, and for good energy savings and a good mix, we put 20 degrees difference. So a 75 degree, which would be very hot thermostat set point in the winter, would be a 95 degree supply. If you used a 68 or 65, you can see you would be 85 or 88 degrees supply air temperature. Now, and then we have no other requirements. Now, ASHRAE 62 says if you don't want to do that, you can put in 20% more outside air. And that, of course, that in certain climate zones, that's a problem. And so it causes trouble. So what we thought was at least by putting this box that was sped back up, that you would have some chance of meeting of getting more throw towards the ground of the hot air that you were producing by the box. So that's one of the ideas we were working on, is to try to help with that situation. Also, again, it just saves a little bit of energy. All right, heating control. So when the economizer, let's see, preheat coils must be off when mechanical cooling or economizer in operation. So we don't want to, we certainly don't want to preheat the air going into a cooling coil, and we don't want, normally you wouldn't try to mix freezing air anyway with the return air. You would probably stop somewhere in that neighborhood, but we don't want to preheat the outside air to mix with the return air, so that wouldn't save energy. Ventilation, air, heating control. Ventilation units operating with other heating and cooling systems shall not supply air above 60 degrees when building load or outside air temperature indicate the majority of the zones require cooling. So what we're talking here is a DOS system, especially if you're running it parallel out to the room. Then we don't want you to do exactly neutral air. So if this air, since you're cooling it down to dry it out normally, then we want you to go ahead and supply it at 60 degrees to the room. That would cause your normal air conditioning system to back up a little bit, and we would take advantage of that colder supply air. If normally DOS systems will do something to maybe come in exactly the thermostat setting, 72, 75, some number like that, and that we feel that's wasteful to try to bring that air back up after you've dried it out. So, and the same thing requirement is applied to outside air that's supplied from the DOS system to the back of the air handling unit itself. If we keep it cooler, it'll back off some of the energy used by the air handler. Duct and plenum insulation. This is we have minimum requirements for duct and plenum insulation in the code. This is the table for the code. You can see it's by climate zone. And so we're looking at where you'd normally be heating and cooling, and then it's by supply and return ducts for heating and cooling, the blend, supply and return ducts for heating only, and supply and return ducts for cooling only. So again, by climate zone, and whether the duct is located outside of the building, whether it's located in unconditioned spaces and buried ducts, or if it's directly in the conditioned space, we have different values. But again, they're minimum values, and these are very reasonable values. Air supply, design, and control. So this is, again, is a table of contents. So if you're using this and you need to find a section that applies to a problem you're working on, here's a list of the sections. But this major section, section 653, is air system design and control, and then those are the subsystems. First subsystem is fan efficiency, new for 2013. So the design total efficiency must be greater than or equal the maximum fan total efficiency within 15 percentage points. So up here at the peak efficiency, back or forth, 15 percentage points is where you're supposed to pick your fan from. And then the AMCA, amca.org is a good site to look at, but they came up with a fan efficiency grade, a FEG. So each fan is graded for fan efficiency, and ASHRAE 9.1 requires a grade greater than 67 for the fan you select. Now, this AMCA ran into some trouble with this grading system. We bought off on it and we put it in 90.1, but we're aware that they ran into some trouble with it. There were certain fans that once all the fans started getting tested, did not do as well as they should have. They were energy efficient fans, but their grades did not show it. And so they've come up with a new system, and they've been working with the DOE to get that system approved and out. And we're waiting for the DOE to agree to it before we put it, because obviously we're not happy that we agreed to this one and then it turned out not to work, or the manufacturers turned out not to be satisfied with it and it not to actually work. And so we don't want to do the same thing again. So we're waiting to make sure, and that approval progress has slowed down a little bit in this change of administration, but hopefully it'll come out soon. Fan power table. So this is one that's been in for a long time. This is actually an old table. It's been modified once, but we still see a lot of trouble, not a lot of trouble because of the modification, but people still this is one of the things that are more difficult to comply with, or we get a few complaints about, or just sometimes get ignored a little bit. But we have a maximum CFM per horsepower allowed for fan sizing. So the first is for first column is for constant volume, and this column, you can see that the simple way, fan system based on nameplate horsepower is just the CFMs times 0.011. And then you just multiply that out and you look at the horsepower, and if that number is greater than the horsepower number, you're fine. Brake horsepower, it gets a little more complicated in the CFMs times 0.094 plus A. Now the reason this number is bigger is because a variable speed fan is not normally operating at full speed. So we give it a little break there. And here's what A is. A is the sum of the pressure drops times CFM through the device that's causing that pressure drop divided by 4131. And where that pressure drop is, each pressure drop adjustment from table 6531-2 in inches of water column, and again the design flow through each device on the table. So let me show you the table. Here's the table, and so these are items that cause normally some pressure drop, but that might be necessary in a well-designed system. And so what we do is we allow you to make some adjustments if you're doing these items. So you would take those adjustments and you would add them here. So you get a little extra brake horsepower. So since we added this brake horsepower section, we've got very few complaints, although we do still get some about this being too strict. Anyway, so then if you move over to the variable volume, you have exactly the same equations, just a little bit more, again, since variable volume allows a little bit more, your multipliers are a little bit bigger than the constant volumes. Okay, so option 2 has one more thing. So you go through, and then so here's what a fan horsepower is. Let's make sure we understand that. So this would be horsepower or brake horsepower. It includes the supply fan. It includes the return fan. They operate at design conditions. It includes any fan that operates in design conditions, such as a series fan-powered box. It includes any exhaust fan from the area being served by that supply fan. The supply fan is the fan with the coil on it, and that's where you get the system CFM. It's this fan CFM. If you just have an exhaust fan inside the plenum that's churning air, you don't have to count it. And if you have a parallel fan powered box, you don't have to count it. If you have a relief fan, traditionally we would always say you don't have to count it. But if that relief fan, due to the amount of outside air you're bringing in, actually does have to run, even when we're not in economizer, then you need to consider adding it. Now, so it's not specifically excluded anymore, but the theory is that you won't need to add it, and we don't really have in my opinion, we don't have a really good way to tell you to add, 10% of the fan horsepower or something. So generally, until we get better rules, I would say you'd get by with just ignoring a relief fan that had to operate in some way when the economizer's on. But if you know it's operating and going to be 50%, then you should probably list it just to be safe. So let me see. All right. I should be telling you about a motor. Maybe it'll come up in just a minute. Basically, we let you skip a motor size. Also, if you use the brake horsepower and your brake horsepower is too close to the next motor size, we let you skip a motor size. But you have to pass the test that brake horsepower is low enough. It doesn't mean that you're going to get out of making that brake horsepower meet. It's just that the horsepower fan you have to pick, if can be a size larger, so that you don't have to pick a fan. Good engineering practice would not pick the fan that's just a slightly larger than the required brake horsepower. But anyway, new for 2013. This matches the steps. So the DX and chill water units controlled directly by space temperature, that's the thermostat, shall have a minimum of 2-speed fan with a low at 66%. At low speed, the power has to be less than 40% draw. A DX system and chill water units to control by space temperature by controlling the space temperature by varying the airflow shall have, or a VAV type system shall have the modulate the fan speed at a low of 50% fan speed, and you have to have 30% power at that point. Now, there's only two mechanisms to do that we know of, and that's either a variable speed drive or a vane axial fan with adjustable blades. So those are the only two that'll meet the 30 by 50 by 30% rules. So generally, that requires a variable speed drive. Static pressure sensors in VAV systems. So we did a strange thing in 2013, or it sounds strange. Instead of fighting with people about putting the sensor 1/3 of the way down the duct or 2/3 of the way down the duct and all the rules we used to have, we just said sensors controlling fan must be located that the set point is 1.2 inches of water column. And then we said if this results in a sensor being located downstream of major splits, multiple sensors shall be installed in each major branch. Exception system using 65323. So here's 65233 VAV set point reset. For systems with digital control at zone level, set point must be reset based on zone requiring the greatest pressure. The set point is reset lower until one zone damper is nearly wide open. So what that means is that we're going to slow that fan down until one VAV box becomes 100% open. When it becomes 100% open, then we'll stop slowing the speed fan down and we'll start speeding it back up. Now, we don't control the fan per the box position. We control the static pressure sensor set point per damper position. So the way we'll speed that fan back up is we will change the set point so it won't be satisfied. So we would raise the set point if that damper was a full open, and that would mean the fan would speed up to get to that set point and the damper would close. So we are monitoring the position of dampers, but we're controlling the set point on the duct pressure sensor. Return and relief control, new for 2016. Return and relief fans used to meet section 65115 shall comply with the following. Relief air rate shall be controlled to maintain building pressure either directly or indirectly through differential supply return airflow tracking. Systems with constant speed or multiple speed fans shall also be allowed to control the relief system based on outdoor air damper position. Fans shall have variable speed controls or other devices that will result in total return relief fan demand control of no more than 30% of total design power at 50% of the total design flow. So what we're saying is that you're going to put a differential. So always when we're trying to pressurize a building, we'll have the supply fan supplying X CFM and the return fan returning X minus some number CFM. Because then the rest of the CFM is used to pressurize the building. So all we're doing is we're requiring supplier airflow tracking because that minimizes the energy used in a system that has both a supply and a return / relief fan or a return relief fan that's in, you know. So that's the requirement as we're telling you how we want that controlled, and we would let you control based on outdoor damper positions for multiple speed fans that aren't required to have VFDs. Parallel fan flow powered VAV air terminals. This again is a new requirement for 2016. Parallel flow van powered VAV terminals shall have automatic controls configured to turn off the terminal fan except when space heating is required or if required for ventilation. So if we don't want that, well, parallel fans aren't supposed to run in normal operation, so they would only run in heat, but it makes sure that you're not doing some sequence that has it run in other situations. Turn on the terminal fan is the first stage of heating before the heating coil is activated. And during heating for warm-up or setbacks control, temperature control, either operate the terminal fan and heating coil without primary air or reverse the terminal damper logic and primary air. So what we're saying is that if you're if room's calling for heat, before you turn on the coil, you'll turn on the fan and pull plenum air, warmer plenum air, and mix it with the minimum supply air and supply it to the room to see if you can heat that room without ever turning on the heat. And that's your first step. During heating for warm up or setback temperature control, what that means in the morning, you come in the building and maybe you're better off not turning on your main supply, especially if you don't have any heat in that unit. If you're just going to supply 55-degree air down the duct, then maybe you're better off turning on the fan and the heating coil in the VAV boxes and just use those to heat the space, not turning on your main system yet. Obviously, if you're not running your main fans, then you're saving a lot of energy. Or if you do turn on your main fans, we hope they would have heat at that point, and so you would have to use a reverse control box or a control logic to say, I'm looking at I've got hot air in the duct, and so I'll open up fully to let that hot air out and use just the primary air instead of running that cold air to the box and then having to deal with it. Temperature reset control. Supplier temperature reset we require all multiple zone HV systems must include controls that automatically reset the supply air temperature in response to a represented building loads or to outdoor air temperatures. We used to have just building loads, and because it's so popular, we require we also change the outside air temperature. You have to be a little bit careful in that because sometimes if the building is not it's got a lot of internal load. Obviously, the outside air temperature really shouldn't be driving the control logic that says that we don't have any load in here. The controls shall reset the supply air temperature at least 25% of the difference between the design supply air temperature and the design room temperature. If a normal design room temperature is 20 degrees, if the supply air temperature is to the thermostat is 55, 75, 20 degrees, then that's 5 degrees. So in used to it, that sentence said 5 degrees. So in what that's allowing is if you do have different supply or room set point temperatures, but basically around 5 degrees. Controls that adjust a reset based on zone humidity are allowed. So in other words, if you're in Texas where I am and you do a reset and suddenly you're not dehumidifying enough, you can take that reset away or readjust it based on a humidistat in the zone. Zones that are expected to experience relatively constant load, such as electronic equipment rooms, shall be designed for fully reset supply temperature. So what that means is I've got an electric room or a computer room or something, a closet, and I've got a box serving it, and the box is sized at a 20-degree delta T for sizing the CFM requirement, and suddenly we reset and now it's a 15-degree delta T, so I'll need more CFM. So you have to make sure that box was sized to operate to cool the room at 15-degree delta T, not at 20-degree delta T. So that will require you to have more CFM in the room. Might be your trunk duct needs to get bigger and your box needs to get bigger. So the reset does have an impact on first cost, or can have a reset impact on first cost. These are not required in climate zones. The warmer, wetter climate zones, 0, 0, 1, 2, and 3. Systems that prevent reheat, recooling, or mixing of heating and cooling supply air. That would be normally a system without any heat in the boxes. System in which at least 75% of the energy for reheating on an annual basis is from site recovery or solar heat energy sources. Fractional horsepower fan motors, ECM motors. We require ECM motors between 1/12 horsepower and less than 1 horsepower, or a minimum of a standard motor that's minimum rated efficiency is greater than 70%. And we can use that electric commutated motor to adjust speed for balancing or for remote control, since they come with automatic adjustable speed. New for 2016, ventilation design. The outdoor air design should be based on ASHRAE 62 or 170, which is the hospital code, or a standard or code that applies to that type of facility. The design must limit outside air to no more than 135% of the calculated outside air, or the design can return to the required outside air with a single set point adjustment, or the system includes exhaust energy air recovery. So what this says is that you cannot put in extra outside air to get a point for lead or something that's going to cost a lot of energy. You will let you go up to 135% of extra outside air, but for room quality purposes, at the expense of energy, since we are an energy standard, we draw the limit at 135% of what you calculated. Or you can go ahead and put more air in, but you got to have a single button that can be pushed to say, man, we're not meeting our requirement. We're using a lot of extra energy. Our demand's very high. Push one button and reset that outside air back down to the minimum required. Or if you're using exhaust energy recovery, so you need a certain amount of relief air for the exhaust energy recovery to work properly, and you're getting work from that exhaust air, we'll let you increase it some. Energy recovery. So here's what we're talking about energy recovery, and you can see we're fairly aggressive in energy recovery. So this is a system that operates less than 8,000 hours per year. If you're between 30, let's say 20 and 30% outside air, so across the top of the form, 20 and 30% outside air, and your design supply fed airflow rate is in climate zones 0A through 6A, greater than 16,000 CFM, then you have to put energy recovery in the space. You can say there's none required uh, up in the colder zones, and then in 6B it's quite a high number. But down here in 7 and 8, where it's very, very cold, it jumps again to be required. Now this changed. These are the changes made in 2016. This little corner we modified. So these numbers between 2013 and 2016 did change down here in the red box. And there are many exceptions, including heating in climate zones 0, 1 and 2, cooling in climate zones 3C, 4C, 5B, 5C, 6B, 7 and 8, and any system that has less than 75% of the usable exhaust locations within a 20-foot radius of each other. That is a new requirement, exhaust locations within a 20-foot radius of each other. Used to, it was 75% in a single location. Now we've changed it to say within a circle. So what this is because we have to cost justify our requirements, and if you had to run duct all over the roof or all over the top floor of plenum to connect these exhausts to each other, then we wouldn't get good paybacks. So what we're trying to do is to acknowledge the savings we get by doing this. At the same time, we're reasonable about what we require you to do on a first cost basis. Now here's the same table at over 8,000 hours, equal to or over 8,000 hours, and you can see that 20 and 30 for that same area has dropped down to 2,000, and that's now still required in climate zones, in the B climate zones. So it makes a big impact, obviously, how many hours a year you're going to operate. Now, exhaust systems, transfer air. This is new for 2016, and it feeds off of what we did in 2010 for kitchen hoods. So conditioned supply air delivered to any space with mechanical exhaust shall not exceed the greater of. So here you've got a room with an exhaust fan in it. And here's how to supply air to the room. The supply flow required to meet the space heating or cooling load. The ventilation rate required by the authority having jurisdiction, the facility environmental health and safety department, or ASHRAE 62, or the mechanical exhaust flow minus available transfer air from conditioned space or return air plenums on the same floor, not in different smoke or fire compartments, and that at their closest point or within 15 foot of each other, available transfer air is that portion of outdoor ventilated air that is not required to satisfy the exhaust needs, is not required to maintain pressurization of other spaces, and is transferable according to the codes and standards of the class of air recirculation requirements of ASHRAE 62. So it's good air. So what this is asking you to do is to make sure before you put extra air into a space that's just been heated or cooled just to be thrown out through an exhaust fan, that you've explored these other ways to make up that fan and still cool the room or heat the room or keep it comfortable. And transfer air is an especially good idea in those cases. So these are the exceptions to that requirement. Biosafety level classification 3 or higher, vivarium spaces, spaces that are required by applicable codes and standards to be maintained at positive pressure relative to adjacent spaces. For spaces taking this exception, any transferable area that is not directly transferred shall be made available to the associated air handling unit and shall be used whenever economizers or other may exceed the available transfer rate. Uh, Spaces where the demand for transfer air may exceed the available transfer flow rate and where the spaces have required negative pressure relationships. For spaces taking this exception, any transfer air is not directly transferred shall be made available to the associated air handler and shall not be used whenever economizer or other options do not save more energy. Exhaust system. So here we go back to the kitchen hoods, and the kitchen hood is set up pretty much the same way, where you have to either use a kitchen hood that has a variable speed on it, where it's looking at the heat of the air coming off the kitchen hood, cooking appliances, and increasing or decreasing its speed based on that, or you're going to transfer at least 50% of the air to a kitchen that exhausts more than 2,000 CFM. So, I'm sorry, 5,000 CFM. At least 50% of all replacement air is transfer air that would otherwise be exhausted from the rest of the building. Maximum exhaust hood for kitchen hoods. This is for 2010. Now, this table looks just like the table in the NFPA or in the building code, but if you look at it, it is the maximum net exhaust flow rate, CFM per linear foot of hood length. The one in the building code or the NFPA is the minimum exhaust flow rate, CFM per linear foot of hood length, and ours is for a certified hood. Theirs is for a non-certified hood. So if you have an engineered and certified hood, this is the largest amount of air per linear foot will allow you to suck out of it, because anytime you're sucking air out, you got to make it up, and it's an energy user. Performance testing on hoods is a requirement, and the reason it's the only requirement for performance testing we currently have in the mechanical section. The other sections are starting to populate some other performance testing, so this is the only one we've got so far. Laboratory exhaust systems. The laboratory exhaust systems haven't changed in a little bit. Now, the laboratory exhaust systems require either energy recovery or a variable speed system. And at this point, we've combined the two into one simple equation. So either by variable system, so you can reduce the amount of exhaust and make up airflow rates, or by sensible heat recovery effectiveness based on the exhaust energy recovery. The combination of those two need to reduce the energy by more than 50%. So we let you combine those. Door switches. Any conditioned space with a door, this is an outside door leaving the building, heating reset point has to be less than or equal to 55 degrees if that door is left open by more than 5 minutes, or cooling needs to be set up to 90 degrees if that door has been left open for more than 5 minutes. This the big thing is that you put a closer on that door, and you don't have to do this. So make sure that you get closers on all those outside doors, because this is kind of a expensive solution to a little problem, in that we're going to put a sensor on every door and send it back to the controls and reset our unit and everything. So you're better off avoiding that. Refrigeration, new for 2013. In 2013, we took the Energy Star refrigeration requirements for the type of equipment that would either be in a restaurant or a 7-Eleven or a convenience store or any equipment like that, and we wrote some energy codes or some energy requirements around it. What we basically did was we picked up the energy store requirements and just codified them. So what I say, instead of reading all this to you and going through each slide or each paragraph, is if you buy a piece of equipment that has the Energy Star on it, then you will automatically meet these requirements because these are straight out of Energy Star. As a matter of fact, this equipment is regulated by the federal government through the Energy Star program, and we don't have the right to change the requirements for this type of equipment. So that concludes the mechanical section. We'll come back in a little bit and do service water heating, a couple of things, but now we'll let Joe start the envelope section.
Hello, Brian, can you pass me the control of the, oh boy, here we go. Okay, building envelope requirements in 90.1 2016. I'm mindful as I'm presenting this that from what I can tell, virtually every one of the attendees of this particular course is consulting engineer or similar, and we don't have half the room filled with architects. So I'll be trying to present this material as requirements for the building envelope that an engineer might see coming from the architecture department or the architectural firm. And for if you're doing whole building energy compliance, either with the energy cost budget method in section 11 of the standard or in appendix G for exceeding the standard, the building envelope compliance needs to be submitted for approval before such analysis is done for the whole building. So some background. Let's see if there we go. So the presentation covers the structure of the envelope requirements, trying to give you a feeling for the mandatory and prescriptive requirements. Then we're going to spend most time on the prescriptive requirements, a little time on the mandatory provisions. They're very important, but there are not many of them. And then we'll go quickly over the building envelope trade-off option, which is very new, but not widely used yet. So the structure, sorry, of the envelope prescriptive requirements has three parts to it, and they're all shown on this diagram. You have 9 climate zones, which is new for 2016. From 2004 to 2013, we had 8 climate zones covering North American locations, and for the third of this audience is in Canada. Sorry, the map doesn't include Canadian locations, but maybe another map will shortly. So we have 9 climate locations. The new climate location is zone 0A, extremely hot and humid, zone 0B, extremely hot and dry. These do not apply for any of the locations we're talking about, but in Southeast Asia or in Latin America or Central Africa or Kuwait, Saudi Arabia, the climate zone 0 has an impact. So we have climate location, and the chart shows the colors going from Florida and southern Texas, climate zone 1 for red, climate zone 2 along the Gulf Coast, the orange climate zone 3 from the Carolinas all the way into much of California, climate zone 3, climate zone 4 going from the southeastern Pennsylvania, New Jersey, through the DC area, and then across the center of the country, and then up through Oregon and Washington State along the coastal areas. And then climate zone 4 in northern Pennsylvania, northern Ohio, much of Michigan, southern Wisconsin, actually. And you see then climate zone 6 and 7, and 6 would also go to Toronto, and we'll see that later. But these are the various climate locations, very important from determining your prescriptive requirements. Then there's space conditioning categories. There's non-residential, residential, and semi-heated. And semi-heated is for industrial and warehouse. Residential is usually as stringent as or slightly more stringent than non-residential. I'll be assuming that most of you are dealing predominantly with non-residential or with high-rise residential. So we'll go through that. Very important for prescriptive compliance is the number of classes of construction, both for the opaque elements, and we see that, whoops, sorry, I hit my, damn, sorry, I should not do that. You'll see on the left the classes of construction for roof and for above grade walls and below grade walls. The real importance of the classes of construction is that all of the prescriptive requirements in the standard are set using life cycle cost economics determined by the economics of the committee. And there's an attempt to pick the minimum life cycle cost economics for the committee's perspective for each type of construction. And the type of construction strongly influences the cost of the insulation that's being used. So this is really important. So let's go to the climate category for the envelope requirements. Here's the map of the US showing the continental US, showing from 2004 to 2013 the 8 climate zones for 90.1, and you can track them. Every county has a single climate zone. This can produce some strange results, like where I live in the San Francisco Bay Area, the county goes from the coast over the hills into the Central Valley a bit and has remarkably different climates, but it's all within the same county. And then in 2016, a major piece of work was done by Standard 169 and produced in 2013, made its way into 90.1 in 2016 with the 9 climate zones. What you don't see here, but we have a map that was produced by Pacific Northwest National Labs that shows the change in climate zones by county, and many counties have gone to a warmer climate zone. And just very few counties in northern Oklahoma, I believe, have gone to a higher climate zone. So we're seeing changing climate has an impact, and but I can't show it to you here. So this is the new set of climate requirements. And then here is the world climate zones. And for the Canadians present today, you can see by color which climate zones are impacting. So a lot of central Canada has climate zone 7. And then southern Canada has, in the eastern part, has climate zone 6A, or mainly 6A. So you can also see the gray, the light gray in Central Africa, which is extremely hot and dry, and up through Saudi Arabia, in the Gulf up through Kuwait, and northwestern Australia, etc. Now, a very simple tool that's available from UCLA, Murray Milnshop in UCLA. It's the Climate Consultants, and it uses EPW weather, hourly weather for a year, and produces some interesting graphic results and some analysis for design strategies. Here is a climate psychrometric chart for Norfolk, Virginia, and it shows the blue boxes on the lower right, the climate comfort zone for ASHRAE. And it goes from 10 degrees Fahrenheit up to 110 degrees. And each dot on this psychrometric chart represents an hour of the year, show you the range of temperature and humidity conditions over the year. And the orange box shows you the impact of internal heat gains in a typical building, increasing the comfort conditions for a building by going down to about 55 degrees. And you can use different strategies for increasing the comfort conditions. So Mac and I use this as we present in different locations around the country, and we have a number of these charts. Dew point, when things sweat and get sticky, we pay a lot of attention when we're in climate zones that have dew points going above 60, above 66, and I think so we know when we have problems. So here's San Diego. We don't have problems with dew points. It's 60, 65 at highest, which are the green dots. Then if we go to Jacksonville, Florida, we find there's about 4 months of the year when we have dew points in above 70, and we have to produce comfort conditions, we have to take care of that situation. And then here is Washington, D.C., where July and August are problematic. And I've lived in D.C., and I know that August can be quite nasty. So we use this information. Yakima in the high desert up in Washington State has no problems with dew point, as we can see with dew point below 50 pretty much year round in the high desert. So that's a summary of climate impacts on the prescriptive requirements. We then go to classes of construction, where we have 3 types of roofs, including insulation above roof deck, metal roof, building roofs, attic roofs with wood steel framing, which lay in insulation below the framing. 3 types of that. Above grade walls, we have mass walls, which would be typically 7 BTUs per foot square per degree F or greater. We have metal building walls for metal buildings, and then importantly for light frame construction, steel frame walls with wood studs or steel studs and wood frame walls with wood studs. Below grade walls, we have several types. And for roof assemblies, here's a typical construction examples from Appendix A in the standard. And there are pre-calculated assemblies that are provided for each class that you can use. You're supposed to use those pre-calculated assemblies for typical construction unless your construction is radically different, and then there's a calculation procedure you can use. Graphic example of pre-calculated assembly shown for each class. Here's a mass wall with stucco, rigid insulation outside, mass wall, and then details for a metal building. And then very importantly, typical construction for steel frame and wood frame construction. Throughout many of the climate regions, it is required to have both insulation between the studs and continuous insulation outside the studs. And both types are needed. You can use options where you have just continuous insulation outside the studs and nothing in between the studs. There are many options, but rarely in 2016 can you get by with compliance with just insulation between the studs, either for steel frame or wood frame. We'll see this. Here are floor options: mass floors, steel joists, wood frame, slab on grade floors, heated and unheated. The requirement for unheated is not real strong in the southern part of the U.S. We'll see that later. So here are the three classes of floor assembly. Here's carpet on concrete slab, and then either steel or wood frame floors. There are slab on grade examples of what is permitted. The standard permits vertical insulation on the slab, but does not like horizontal insulation in the non-permitted examples below. So for fenestration construction classes, in 2004, there were just two types of construction class: fixed windows and operable. In 2007, that went to non-metal framing of all types, metal framing curtain wall, metal framing all other, and metal framing entrance doors. Entrance doors with any glass in them are so difficult to have a rigorous insulation value that it's much less rigorous in its compliance requirements from the other types of fenestration. And then in 2013, I think the types of construction classes was refined a bit, and you have non-metal framing all, that would be wood or vinyl, or some other type that's non-metal, metal framing fixed, metal framing operable, metal framing entrance doors. So these are the four construction classes for windows. And then for so that we've covered climate, construction classes, space conditioning categories. Essentially, you have exterior envelope, which is the darker tinted envelope that surrounds conditioned spaces, and semi-exterior envelope where you have semi-heated storage, and you have requirements both for the surfaces facing into the conditioned space and facing into the outside. For ventilated crawl space, it's effectively outside. For ventilated attic, it's effectively outside. So you have all of these different conditions as part of the requirements. So if you have a complicated building design presented to you by your architect, you can use these categories to determine what the requirements are. Now, let's go to the prescriptive requirements and start into that. This is a major section, and we've hit the 1 hour point, and let's take a 5-minute break at this point before we start into that. So we'll stop. It is now 2 minutes after the hour. We will go, or 3 minutes after the hour, we'll go to 8 minutes after the hour and start up again. Talk to you in 5 minutes.
Just want to remind y'all to ask questions. Just chat up, type them in, and we'll try to answer them as soon as we can. We don't have any questions yet. We must have been perfect, Joe.
Absolutely. Well, we're getting into some interesting parts of the envelope compliance. This is, we see, see if I can do this. Nope, can't do it.
Well, we do have a couple of questions. I
Do
forward them
we
over to
really?
Mac. Yes, I forward them over to Mac.
Okay. All right, here we are with screen 196. This shows a building envelope requirements table. This table is one page in the standard that contains all of the prescriptive requirements for climate zone 1. So if you're in climate zone 1, like if you're in southern Florida or Hawaii, you can carry this table around and it lists all of the requirements for climate zone 1. And it's the same type of table for each of the 9 climate zones. The only thing that changes is the values of the numbers inside. You have the same structure in each table. The top 2/3 of the table are the requirements for the opaque envelope in pink, and the blue in the bottom is for the windows or fenestration and skylights. One important thing to look at, and it's hard to see in this, is that your fenestration, your vertical fenestration is limited to 40% of the wall area or less, and the skylight area is limited to 3% of the roof area or less. If your building has more glass than these limits, you can't use the prescriptive requirements. You must use the whole building requirements in section 11, the energy cost budget method, which again will limit you to 40% window wall ratio for the base case building, which meets the requirements of the standard. So if your architect is coming to you with a building at 60% glass or 70% glass, or even more, as I see as I walk around Washington, D.C. or Toronto or areas in Florida or Texas, many new buildings have a higher percentage of glass. This presents challenges for compliance because you must use the whole building approach, either an ECB or Appendix G, and your baseline building that you're complying against is going to have 40% glass, or if you're using Appendix G in 2016, depending on your building type, it could be 32% glass or 25% glass or even less than 20% glass as a baseline. So the amount of glass can impact 10 to 20% of the total building energy difference. So it's a really important factor. So with that proviso, let's go on and look at prescriptive requirements for the opaque envelope. And you'll see up in the upper right for this slide that we're down in Florida and also southern Texas. And here we are in climate zone 1 here. But this shows you stringency requirements from 2004 to 2016. And ignore that it's just climate zone 1. This table covers all of the climate zones from 0 to 8. And if you started out in 2004, the R value requirement for insulation entirely above deck was R15, except for climate zone 8, where it was R20. But by 2016, which we're talking about today, the requirement for climate zone 0 is R25. For climate zones 1, 2, and 3, it's R20. Climate zones 4 and 5, it's R30 and also 6, and then R35 for climate zone 7 or 8. So there's been a major increase in the stringency of the opaque envelope requirements, and pay attention to the requirements in climate zone 0, 1, 2, 3. A little later on, we'll look at the white roof requirements and what you have to do if you don't have white roofs in climate zone 0 through 3. And then for metal building, you see you have two sets of insulation requirements in the metal building structure. And for attic and other, you have very high requirements because the lay-in insulation is much cheaper to install. You have R38 climate zones 1, 2, 3, 4, R49 climate zones, climate 0 through 3, R49 climate zones 4 through 6, and climate zones 7 and 8, you have R60. So you can see that there's been a major increase in stringency for opaque roofs. For walls, it's very similar. Let's go to steel frame and look and use that as an example. In 2004, it was R13 up through climate zone 4, and then you had to, in climate zones 5, 6, 7, 8, you had to add continuous insulation outside the studs in addition to the insulation between the studs. I was just starting in climate zone 5. By 2016 for steel studs, only in climate zone 0 and 1 do you have insulation between the studs alone, and this would be for 2x4 R13. And as soon as you get to climate zone 2, you're adding insulation outside the studs, continuous insulation in addition, and the thickness of that continuous insulation keeps increasing as you go to the colder climate zones. So you have in climate zone 4, continuous insulation are 7.5, climate zone 5, it's R10, climate zone 6 are 12.5, climate zone 7, it's the same, and climate zone 8, it's R18.8. So you see that there is a major increase in stringency of the opaque envelope, both roofs and walls. Now, what does this mean within the table? And so here we're taking a close-up look of climate zone 1 for opaque envelopes only. This is the top 2/3 of that table 5.5-1. And you can see that in the red outlines, we have non-residential construction on the 2 columns on the left, residential construction, the 2 columns in the middle, and semi-heated spaces, the 2 columns on the right. And you have 2 ways you can go. You can comply either with the U value requirements or with the R value requirements. You don't have to comply with both. You choose which one you want to comply with. So the committee has gone to great lengths to try to make this as flexible for you as possible. And then here are the 3 rows for roofs, and you have the R value for insulation above deck and attic and other metal buildings. Walls above grade, you have the different requirements in climate zone 1, walls below grade, floors, etc. Now here is the table in 2016 for climate zone 0. And here are the non-residential requirements. So R25, continuous insulation above deck, that translates to a U value of 0.039. And then R38 for attic and other insulation, lay-in insulation below the structural framework, 0.027. So if we go to climate zone 1, you can see the change in values here. I'm not going to go through this, but each of these tables show the area of the continental US or Alaska where it applies and the values. And we've intentionally included all of these tables. So even if you don't have the standard at your desk, you can go and find these values by looking at the PDF file you can download from the ASHRAE website. So here we go, climate zone 4, climate zone 5, climate zone 6, and 7, and 8 up in Alaska. So these are all of the different conditions. And that set of tables shows you the summary of the R values. I haven't produced a similar table for U values, but it shows you the R values. Now, as I said before, if you're complying, you can comply using the R values. In this compliance, you're using only the thermal transmittance of the insulation layers within 2 locations, the insulation within the framing cavities or as continuous insulation without the framing breaks. So at some time in the past, some members of the Standard 90.1 committee did some hot box tests and determined that the steel stud insulation effectively cut the insulation effectiveness by 50% if you only had insulation between the studs. So this led to having insulation, continuous insulation outside the studs. And there are building science experts that argue that you should put all your insulation outside the structural members. So it's your choice though. And then thermal transmittance is not included when you're using R values for the other building materials in the assembly or for the air film. And the insulation extent is over the entire surface that you're concerned about, and it's to the level, to the intended R value rating. The R value rating is not an average, it's effectively a minimum. All right, and then if you're using compliance using the U factors, the compliance is for the entire assembly. And there are pre-calculated values in Appendix A that shall be used. You're supposed to use these pre-calculated values, or if you have an assembly, and here are all the tables that are listed in Appendix A for U factors, for C factors, for F factors, depending on what you're looking at. And for assembly significantly different, you can calculate the values, and there's rules in Appendix A9, and these must be approved by the building official. And there's a summary tabulation of required procedures shown in the user's manual. Incidentally, I strongly recommend, if you're doing compliance with Standard 90.1, that you have at your desk a version of 90.1. For example, I've got on my computer right now, open somewhere here, a PDF of the entire standard electronically, which you can get. And you also would want to have a copy of the user's manual. I recommend both of these. You could get by with just the information we're presenting in this presentation, but if you're supporting your architects for the envelope compliance, you will want to have this information. And here's an example of the above grade wall compliance calculation using R values and converting to a U value. It's got a couple interesting spelling mistakes. This is from the user's manual of a couple generations back, but shows you that your data sources for almost all of the layers are coming from Standard 90.1 tables, and only the rigid insulation is coming from the manufacturer's data. So shows you the method for doing it. Also shows you the method for calculating heat capacity for mass walls. And as I said before, you must use data for typical assemblies from Appendix A. Here is a very handy table that's hard to read because there's so much crammed into it. But here's for U factors for steel frame walls. On the left, you have steel framing 16 inches on center, 24 inches on center, 3.5-inch stud depth, 6-inch stud depth, and then different baseline insulation levels between the studs. And the third column in gives you the overall U factor for the entire assembly. Then as you begin to add R value of continuous insulation outside the studs, this table gives you the equivalent U value for the R value that you're using. So if you have 3.5 inch studs, R13 between the studs, and then you add R10, continuous insulation outside, your total effective U value is 0.055. Good information, and Appendix A is full of this type of data. So this is the basic approach for compliance with the opaque portions. Now, in climate zones 0, 1, 2, and 3, and this is effectively the areas on this map that are in pink or bright orange or modest orange. For North America, these are the areas 1, 2, and 3. So for roofs in these areas, climate zones, and this should say climate zone 0 through 3. But what you have is you have a new approach which has a minimum 3-year age solar reflectance of 0.55, and a minimum 3-year age thermal emittance of 0.75, and it gives you this the Cool Roof Rating Council standard that you use to test this. A minimum solar a minimum solar reflective index of 64 when determined with ASTM E1980 using a convective coefficient of 2.1 BTU per hour per foot square. Again, based on 3-year age solar reflectance and thermal emittance data from the CRC1 standard. You either have these white roof requirements, or you have to increase your roof insulation levels as shown on the next slide. So if you're in climate zone 0, you must go with an insulation R value above 36 R36, and that's compared to R20 or R25 in climate zone 0. In climate zones 1, it was R20, you must go to R33. So if you're not using white roofs in these 3 climate zones, you have to use substantially greater levels of insulation in the roof. It's the basic message here. Does not apply to climate zones 4, 5, 6, and greater. You can do your own life cycle cost analysis to see if the white roof will pay off for you in those other climate zones. I suspect climate zone 4 and even 5, you would find it quite useful. Okay, we've just completed the prescriptive requirements for the opaque portion of the envelope. Now let's look at fenestration. And this is in section 554 of ASHRAE Standard 90.1. The items covered include a simplified approach to windows, solar heat gain coefficient, SHGC, and U value criteria. You must use the National Fenestration Rating Council standards or the European equivalent, the ISO equivalent. These are rated. You have an unrated window option, but it's very difficult to meet. So this is your compliance method. We'll see this in a bit. You get credit for permanent external shading, and there's an exemption for street level fenestration that there are no SHGC requirements if several conditions are met. And this exception, I've walked along the streets in Vancouver and other places and seen where this exception pays off. So for glazing types, you're looking at spectral control of the transmission of light and heat through the window, where you want to reject the near IR heat, but you want to capture usually as much daylight as possible. and you get you try to choose windows with maximizing daylighting with only half the solar gain. You use insulated IG or insulated glazing units to minimize the solar heat gain coefficient. So the yellow is what you want, and the red and you don't want. So the technologies you can use are selective absorbers like blue-green tints, which right now are not permitted as an option for the prescriptive compliance. You can use blue-green tints in whole building energy analysis options, but not for prescriptive compliance. And I'll show you why on the next slide or next two slides. And then you have selective reflectors, modified low E coatings. These have become very widely used and reasonably cost over the last 20 years of standards development. You have coated glass and plastic and multi-layer dielectric. These are all the different versions you have of glazing. I like this chart because it shows you some basic relationship for many, many insulated glass units. And this is from a Lawrence Berkeley National Lab International Glazing Database, IGDB. Each dot here represents some manufacturer's IG product. And along the horizontal axis is the solar heat gain coefficient. Along the vertical axis is the visible transmittance, TVIS. And so you can see the relationship between the two. The vertical red lines show you the solar heat gain coefficient requirements by climate zone for standard 90.1 2016. So starting in climate zone 0, the new climate zone, you have an SHGC of 22, solar heat gain coefficient of 22. For climate zones 1, 2, and 3, you have a solar heat gain coefficient of 0.25. So you have 0.22, 0.25 for climate zones 4, 5, and 6, going from New York up through Toronto, etc. You have 0.4, and in climate zones 7 and 8, you have 0.45. You have some limitation on the solar heat gain coefficient in all climate zones. And that means that only the glass products to the left of the red line are available for meeting the prescriptive requirements. Again, if you're doing a whole building energy analysis, you can you can use a product that doesn't meet these prescriptive requirements. But in some of the simulations that I've done, you can have a major impact on energy efficiency improvement by judiciously selecting the combination of solar heat gain coefficient, the SHGC, the U value, and the visible transmittance. High visible transmittance for daylighting, as low as possible SHGC in most locations, and a U factor that is appropriate for the climate. And yeah, it can be a major determinant of the effectiveness of the envelope. You'll notice this gray area, the gray triangle at the lower right. This is a new requirement that came in 2013. It exists in 2013. It says that your visible transmittance through the glass must be 1.1 times or over the solar heat gain coefficient. So all of typically tinted glazings like blue, green glazing, the visible transmittance will be 0.7 and not 1.1. So all of these products in the gray area cannot be used for prescriptive compliance. Again, you could use these products in a whole building analysis, but not for prescriptive requirements. So let's look at the impact of changes from 2004 at the top, 2007, 10, 13, 2016. What has been the change in the maximum U value for fenestration assemblies across climate zone 0 through 8? In 2004, Most of the southern climate zones, it was single pane glass, except for climate zone 3. So, and climate zone 3C, which is in the Mediterranean coast of California, was also single pane. And then climate zones 4, 5, 6, 7 had various double pane options. Pretty lenient in those times. It wasn't until 2013 that there was a major increase in stringency of the U value, the maximum U of the fenestration assemblies across pretty much all climate zones. And then in 2016, this was cranked down even more. So it didn't change much in climate zones 1, 2, and 3, but it changed a bit in climate zones 4 through 8. That 2016 was increase in stringency from 2013. And then the new requirements in climate zone 0 are fairly stringent to protect against heat transfer through the glass because of the fairly large temperature difference. If you've got temperature outside of 110 degrees F or 115, you want to protect the glass frame from transmitting a lot of heat into the interior. So then that was for the opaque portion of the windows. For the solar heat gain coefficient, or the solar portion of the fenestration assembly, the requirements were pretty stringent in even 2004, with a SHEC of 0.25 up through climate zone 3, and then 0.39 up through climate zone 6, 0.49, climate zone 7. And there was a variation. You could use less stringent glass facing north. The north-facing variation was removed in 2007, and the requirement for glass facing in all directions was the same at 0.25, and it stayed at 0.25 in climate zones 1, 2, and 3 for the last 10 years, almost 15 years. It's really quite consistent and strong in the southern region. The new climate zone 0 has a maximum SHEC. This should say 0.22, not 0.2. And then in climate zones 4 and 5, and this covers a broad, highly populated area in the middle of the US, the SHEC has been reduced from 0.4 to 0.36 in climate zone 4, and from 0.4 to 0.38 in climate zones 5. This is the only change in SHEC in recent time, and fairly significant. So you should be aware of this if you're doing compliance in the middle regions of the US, etc. Oops. No questions that I can see. All right. Brian, are you shooting these to Mac?
Yes.
Okay. Any questions?
No new questions.
No
Just
new
the two.
questions. Okay. Okay.
Doing a great job.
Well, I'm trying to discuss how the architects can screw up the engineers' work. So
You should know, Joe.
I do know, as you're aware of. So this is going through the fenestration portion of the table. So this is the bottom 1/3 of each of the tables that's on a separate page in section 5 of the standard. It shows you for climate zone 0 what the U values are, and you have a U value for the window. You don't have R values for the window. You have the U value. You have the SHGC, and you have the 1.1 minimum relationship between the visible transmittance and the SHGC. Then here's climate zone 1, And what I've done here is highlight with a red border those factors that have changed from 2013 to 2016. So we can see that in climate zone 1A, the U values have changed. Climate zone 2, U values have changed. Climate zone 3, U values have changed. Climate zone 4, U values have gotten tighter, and the SHGC has gone from 0.4 down to 0.36. Okay, and that's both for non-residential in the first two columns and residential in the middle two columns. And then climate zone 5, as we said before, SHGC has gone from 0.4 to 0.38, and the U factors have gone down somewhat. Here's climate zone 6, U factors only, climate zone 7, U factors only, climate zone 8, U factors only. So this summarizes the various U factor requirements that the engineer should be aware of if the engineer is putting together the compliance package for the whole building, or if the engineer is doing the simulation on a whole building basis, should be aware of these values being input to the simulation program. For the skylight area, there's an interesting requirement that any enclosed space in a building that's 4 stories or less, and that's greater than 2,500 square feet, and the space is directly under a roof with ceiling heights greater than 15 feet, and is one of the following types: an atrium, an office, a lobby, a concourse, a corridor, storage, gymnasium, library, stack area. So if you have a high space, you need to have daylight areas under skylights at a minimum of half the floor area of the space. So you need to have skylights or roof monitors that provide daylight into this space. And where I am in the San Francisco Bay Area, I see a lot of spaces for automobile repair, et cetera, that have such skylights and roof monitors. And it's quite prevalent. So this is a requirement in the standard. There's also a requirement that you have to have, for vertical fenestration, you need to have at least as much glass facing in the south as you've got facing east and west. You can't have your east and west be larger as part of the prescriptive requirement. Not mandatory, it's prescriptive requirement. And then you get credit for external shading, but it's limited to overhangs. You get no credit for vertical fins or for non-permanent devices such as awnings. You can convert the type of geometry you see in this shot to overhangs and to get credit for them. And here's the way you do it. You have a projection factor, which is the H, and H is the height from the windowsill to the bottom of the projection, the shading projection. P is from the exterior surface of the window to the edge of the projection. The projection factor is P over H. And the way this works is that your projection factor goes from 0 to 1. And let's just take a projection factor of 0.5 or to 0.6. You get an SHGC multiplier, which lets you multiply your SHGC for compliance. So if you're in climate zone 4 or 5 or 6, your SHGC, well, no, we'll take climate zone 6. Your SHGC is 0.4. And if you're using an SHGC of glass that's 0.6 because you like the visible portion of it or you like the U value, but it doesn't meet the SHG requirement for the glass by itself. If you have an overhang with a projection factor of 0.5, you can multiply that 0.6 by 0.6 and get 0.36, which will comply. It would also comply in climate zones 4 and 5 that have 0.36 or 0.38. So it's a pretty effective and somewhat lenient requirement, because these projection factors are looking only at the cooling impact of the external shading. So if you do a whole building energy analysis and do external shading, you'll find that the wintertime negative impacts on energy are compensate and negate the summertime benefits of cooling reduction. So you need to look carefully at your external shading. My suggestion for external shading in the northern part of the US and in Canada is to do seasonal shading devices, where the shading device works in the cooling season, but then is retracted in the heating season. I know a building along Market Street in San Francisco that uses such movable shading devices very effectively. And then if glass cannot be avoided, shade it. And this is a southern attitude on shading. So you're seeing that in a hot summer day, that your glass temperature of the unshaded glass is 121 degrees F, where the shaded area is only 88 degrees F. So it's a major benefit of the shading. And then street level fenestration. Okay. Street level fenestration, you have no SHGC requirement if on the street level you have the following conditions. The height of the story is less than 20 feet. This is the street level fenestration. You have a continuous overhang outside with a projection factor greater than 0.5, which means your projection is at least half the window height or more. And on the street side, the street level story, the fenestration area is less than 0.75 of the total gross wall area. If those conditions are met, there is no requirement for SHGC, which means you can use clear glass and maximize the benefit of showing goods and apparel inside of the glass. So it's good for retail stores. And you can also get credit for overhangs that have that are not opaque, that are semi-opaque, and there's some detailed calculations you can do for glazed overhangs, which I have seen again in Washington, in Seattle, and Vancouver. Okay, that covers all of the prescriptive requirements, and I've gone to great lengths to try to indicate what those prescriptive requirements are and what some of the exceptions are. Then for the mandatory requirements, there's some significant mandatory requirements, but there are not many, and we'll go through them quickly. For insulation, there are some requirements about the installation of the insulation and what the product information is, and these sections of the standard tell you what they are. There are also requirements for product information and installation requirements for fenestration and doors. And this even includes sectional garage doors. And there's an air leakage requirement that keeps getting more effective. Up until 2010, the air leakage requirements in Standard 90 were actually pretty weak and not effective. And then in 2010, an air barrier requirement was added to the standard, and it took 10 years to get it into the standard. There was a lot of opposition to it. And in looking back on it, I can see some ways that could have been reduced in terms of the negative reaction to the requirement, but it be that as it may. What the continuous air barrier mandatory requirement is that the entire building envelope shall be designed and constructed with a continuous air barrier. And the exceptions are semi-heated spaces in climate zones 1 through 6 and single-wide concrete masonry buildings in climate zone 2B, which is down in some areas of southern Arizona and Texas. No, actually southern Arizona, western Texas. The requirement includes provisions for continuous air barrier design, installation, and acceptable materials and assemblies. And here are a listing of some of the materials and assemblies. These meet the requirements for the materials and assemblies portion. And here's more requirements that are met. I won't go through all the details on this. The critical thing about the continuous air barrier requirements is that there is not a mandatory acceptance testing during construction where you have to test whether the building is meeting minimum tested conditions for leakage, or there's not specific requirements for design review during the design of the building. So I think that the next stage of this requirement will be when there are effective testing requirements or design review requirements for this requirement. It's coming close, but it's not there yet. It's taken a long time to get. Okay. And then here are a list of mandatory provisions for fenestration and doors, the rating of the fenestration products, the labeling, fenestration, labeling of doors, U factor, solar heat gain coefficient, visible light transmittance. And here is an example of the National Fenestration Rating Council test procedures. These are not standards, they're test procedures. For U factor, it's NFRC 100. For solar heat gain coefficients, NFRC 200. For visible light transmittance, NFRC 200, and air leakage, NFRC 400. Now, what these are test procedures that the manufacturer of the window does or has performed and pays for to produce labels like those on the right, which indicate the U factor, the solar heat gain coefficient, visible transmittance, and air leakage for the window assembly, not just the glass, but the window assembly for typical sizes under reference test procedures. The committee has gone to great lengths to encourage the use of NFRC test procedures. And then vestibules have been a subject of debate within the committee, and each new version of Standard 90.1 adds additional refinements to the requirements by climate zone for vestibules. And again, I won't go into the detail, but it's well laid out in the standard and also examples in the user's manual. And the requirements increase as you go to the north. And here are just some refined examples by climate zone. And further examples. There's a building envelope trade-off option. For 30 years, there's been a trade-off option that was based on regression equations that were done back in 1980. The 2013 and 2016 versions of the standard use a new approach using Energy Plus. And this approach is embedded in ComCheck. And so when you're using ComCheck, you will be using this new trade-off option. And that covers the building envelope requirements. I stress again that they're very important for doing whole building energy analysis, to use these requirements and follow through on the details, and to be very aware of the negative impact on building energy efficiency of use of large glazed areas. You just have to work harder in other parts of the building to make up for the use of a lot of glass. That is it. Mac, I turn it over to you.
All right. It's 53 after the hour, so I think I'm going to go ahead and give you a slightly extended break, and I will start at the top of the hour in about 7 minutes. So if you guys want to take your break now, then we'll take it from there to the end of the program. Thank you. I'll be right back.
Whoops.
All right, we're back. We have two questions. The first question, they date back from the earlier this morning's talk, HVAC talk. The first one is gives a few of the problems with economizers, the added cost of the equipment, the poor performance of the humidity sensors and maintaining the dampers, and asked based on that whether it's the added cost for the economizers and everything are a good deal, and we should rely on them so heavily and as part of the 90.1 requirements. So I'll give you a little history on it. What we did was we ran first DOE 2 models that showed a lot of payback on economizers, and then we had a special, and it was special because collusion between manufacturers, especially on cost data, is a very serious thing. So we had to have a third party set up, and we asked all the manufacturers for rooftop units and different size air handlers and things to submit their costs, their added costs for the economizer to this blind committee that it wasn't a committee, but it was someone outside the organization or an organization outside that organization. Anyway, so that there could be no collusion, and then we took that cost data, that real cost data, or what we think is real cost data, and compared it to those energy savings. Then we went a second step, and we did the same calculations using bin data, weather bin data for the different climate zones, and double check the model requirement on a more simplified equation, but still tied very directly to the weather. And that's the way the paybacks were generated for the economizers. So we do believe that that based on first cost and the savings, they are there. Now, your good points are they've got to work, and there are maintenance costs. We did include maintenance costs, but there are, we're assuming kind of a best world, and we realize that. It's pretty much a pretty good study, though, of what the potential savings would be if everything worked out right. Now, the Army has recently decided that they would not require economizers in climate zones 1, 2, and 3A because of the humidity problem. So they've decided to, they adopt 90.1, but they can take exceptions, and they did take that exception and pulled that out. Our own Appendix G no longer requires economizers in the baseline system you're competing against in climate zones 1, 2, and 3A, or several climate zones, even more than that. Anyway, so let's say there has been some pushback, and we've gone through, yesterday or last week, we did talk about the problems we've had in enthalpy control and the humidity control, and knowing that that's causing problem. On top of that, we've had problems with the humidity, the cost in dry areas of adding humidity to the air that comes from the economizers, and that's why we're working towards a non-adiabatic type system requirement or humidifier requirement, because obviously if you've got very dry air you bring in, you have to raise the humidity in it, then you've eliminated a lot of the savings from your economizer. So we're not unaware, and we're trying to make sure we keep all of these factors in our calculations and our requirements, but you're not off base in at least questioning some of those requirements. Now, one of the things that Joe went through earlier today was that in 2016 we changed the climate zones. So there are several counties at the bottom southern tip of Texas that are in 2016 climate zone 1. And climate zone 1, they would not have economizers. Now, these same counties do not believe the economizers are doing them any good because they're hot and humid climates. And yet, Texas is under the 2013 90.1, and so today they would build a building and have to install the economizer when the weather's the same. It's just that they haven't adopted the 2016 code yet, and they would not have to require that economizer. So they're pretty frustrated when I talk to those people about adding economizers when they know that all it is an adoption. It's not even a change in weather because it's already changed. So there is a lot going on with economizers, but right now and in the foreseeable future, we'll continue to support their use because they do save a lot of energy when operating properly. The second question was about the energy recovery. And the question just asked if I've got 50% outside air, would I always have to use energy recovery? And it's not that easy to answer because you have to use a table with the exceptions to answer that question. And sometimes depending on climate zone, depending on what your supply, how much supply air you have, total amount, then the answer can vary over whether 50% is a number that causes you to have to. But in general, there's no magic percentage that you always have to have heat recovery. And because of the distance to the exhaust, that all the exhausts must be within 20 feet of each other, that's a pretty big exception still. So again, I can't really answer that question straightforwardly, but if you'll look at that table and study it a little bit that's on the previous slide, you'll see when you would have to use it for 50%. And again, if you have some other questions about that, then my email was on that last slide, and I think it's again later, and feel free to email me your specifics, and I'll try to help answer your question. All right, let's get started on service water heating. Whoops, let's see if I can get it started. There we go. So service water heating has the same compliance paths we've been talking about earlier. That they've always had the prescriptive path, which all sections do, energy cost budget, and now they have the Appendix G performance rating path. So there's 3 paths through the service water heating. Now, service water heating, we pretty much have some regulation on every piece of it. Here is a service water heating system with a boiler or a heater and a separate storage tank. So for the heater, we have the efficiency tables that we'll look at and standby losses. For the piping between, for all the piping in the system, we have the installation requirements. We have control requirements for the circulating pump, and we have insulation requirements for the unfired storage tank. And again, we have other requirements for the actual recirculating pump. We require that load calculations be performed so that, again, you know exactly how much water that's required. Again, we do not require you to size your system directly from that load calculation. You have some engineering, you have the capability for some engineering, for your engineering ingenuity to play with that design. Here's a typical table for service water heating, and you'll note that that we have, sometimes we have 2 requirements. We'll have an efficiency requirement and a standby loss requirement, and you have to meet both of those requirements. You don't get to pick one or the other. So that's the key. And again, you could see straightforwardly what our requirements are. 80% is typical for standard gas-fired equipment. HVAC, service water heating, mandatory equipment efficiencies. Hot water supply boilers and water heaters must meet all the standby loss requirements, except where they have a 140-gallon storage tank or larger. So this is a water heater with 140 gallons of storage. Those are not tested in general. So you would have to have a one-off test because those, so we don't require that. We only require the insulation of 12.5, no standing pilot, and fuel-fired heaters have flue dampers or fan-assisted combustion. Insulation for the piping. Recirculating system piping, including the pipe between the tank and a separate heater, is required. Now these are from the requirements are from the 683, which is the HVAC table. So we require the same amount of insulation. If you'll remember, that insulation, this was from last week, is based on water temperature. So based on the water temperature of the domestic hot water or the surface water heating, they use the same insulation values. 8 foot of the outlet piping from a tank or a storage tank type non-recirculating system. Inlet piping between the tank and heat trap on a storage type non-recirculating system. And externally heated pipings, heat trace, or independence heating. Now, all recirculating system piping including the tank, between the tank and the separate heater, have to be insulated. Now, this begs some questions that we've been working on since the 2016 and a little bit during it cycle. So the recirculating system goes out to a commercial restroom, and from the recirculating system, say Plex or some other types piping, runs into the restroom and hits the fixtures. So the part that is not part of the recirculating system, the deadhead piping that leaves the recirculating system and runs to the fixture, is not required to be insulated. Now, how for good design, how long should we allow that to be? And that's being debated now. You'll know in the IACC, they have adopted a requirement that would keep you sometimes as close as 2 foot from the fixture. And this has, we're an energy code. Now there's reasons, if we were a Legionnaire's code, and there are such a thing that are Legionnaire standards, that we might, that if that was our what we were supposed to regulate, then we might come very close to the fitting. But we hope and that we don't, that that's not what what we have been challenged to do. We're an energy code, and saving water obviously is a good thing to do, but we're not actually the water code. So what we're trying to decide is how much energy you save. So we're just looking at how much heat you're losing in that pipe, not how long you'd have to run the water to get the hotter water out, but how much heat we're actually losing through the uninsulated pipe. And that's our direction. Now, some people in the committee think that we should go ahead and be look after the Legionnaires and the water loss, but really we have a purpose and scope that does not cover that, and a lot of us feel like we have to say that. It's not like it's not being covered in the plumbing code. It's not like it's not being covered by other codes, and we just shouldn't. There's the 189 that handles water. In my opinion, we shouldn't be just trying to grab everything we can grab and doing things that really the committee makeup is not built to support those decisions. And there are other groups that are made up to support those decisions. So although we are in debate and looking at what to do about that deadheaded pipe, we haven't done anything yet. Now, for the manufacturer, we require the manufacturer to give you the option to turn the water heater thermostat down to 120 degrees. We do not tell you where to set it. So it's where you're comfortable in setting it. And again, you have to decide what your users are and whether you do have a Legionnaire's problem and all. It's up to you where you set it, but the manufacturer should have on his dial or on his thermostatic control, the ability to allow you to set it down to 120. There's all kinds of discussion about what temperature we should be washing our hands at, and what, we're commercial, so the showers stuff do come in, and especially in high-rise apartments and stuff, but there's a lot of lavatories and things in a normal office building, so there's a lot of discussion going on what these numbers should be. Time switches or other occupant detecting switches for recirculating in heat trace system. So basically, we want to make sure that if the building's unoccupied or that system's not being used, the occupants have the chance to turn off a system and make sure that the recirculating pump doesn't run when it's of no use, or heat tracing systems. Outlet temperature control for public lavatories down to 110. That's the same as the plumbing code again, so that it's in our code, but it's covered by other codes. Circulating pump controls to limit the pump operation of heating cycle plus a maximum of 5 minutes. So the picture I showed you a minute ago that had a heater and then a pump over to a storage tank. Once that storage tank is fully charged, within 5 minutes of it becoming charged, then we want to turn off that pump. Of course, there will be standby losses or maybe some drawdown on the tank that would cause it to come back on, but we don't want the pump just to run all the time and circulate that water. Pool heaters must have on-off switches, not just thermostats. Again, this allows a user to turn it off if they know they're not going to be using it for some period of time. No standing pilots or pool heaters. So for pool heaters. So this is just because we don't think the pool heaters are they strike at a far enough spaced out that the standing pilot would be a waste of energy. Pool covers are required for heated pools and insulated R12 covers if heated over 90 degrees. So this is a requirement, and sometimes this causes trouble because in big commercial installations, or even in, say, a water park, there could be heated pools that these covers are going to be complicated to put on and not used that often during the normal day, but they are a requirement of the standard, and they do save energy in general. If you look at these are all 7.4, so these are all mandatory requirements and cannot be modeled around or anything. Pumps and heaters must have time switches. So again, that we minimize the time they run and minimize if they're not in operation. Now, this is a new requirement that was in the 2013 standard. New buildings with installed capacity over 1 million BTUs, the minimum thermal efficiency of 90%, can use capacity averaged over multiple units, and these requirements went into effect in 7/30/15. So they are in effect. Now, what this requires is condensing boilers. I lost the word condensing for a second. Condensing boilers. Now we've said for many years in the committee that we would never, this is the minimum efficiency standard for all buildings built, and is a minimum efficiency standard. We thought we would never require condensing boilers. It just didn't seem logical. But there are so many condensing boilers being installed in practice today that we believe that even as a minimum standard, for especially if you have a large requirement, that we can require condensing boilers under those conditions. Again, these are fairly prominent now in the industry. So now we're going to look, leave that's the end of water heating. So if you have any questions about that, please get them in. And now we're going to talk about the simplified approach. We did this a little bit earlier, but we want to go into detail of what actually the simplified approach is. So The purpose of the simplified approach is to ease the complexity and compliance burden for 80% of the building permits, consistent with prescriptive requirements. So now here's what we wrote. This was written in 1999, or for the 1999 code. So it's supposed to ease the complexity for 80% of the building permits, because we found out that 80% of the building permits were for buildings 1 or 2 stories, buildings less than 25,000 square feet with single zone systems that were air cooled or evaporate cooled condensers. So we wrote a compliance form that was 1 page long and said this will be, everybody can use this for simple buildings, and we won't, and that's 80% of the buildings, and then the 20% that's left will need all the requirements we've gone through over the 2 days of this conversation. So, but what we put in there was this consistent with prescriptive requirements. That turned out to be a problem. So here's what we have today. We have where we started. A, the system serves a single HVAC zone. B, the equipment must meet the variable flow requirements of 653. So these are all the requirements that we've gone through, all the prescriptive requirements. We have to have a unitary package of split system conditioner that either it's air cooled or evaporate cooled, and the efficiency must meet the tables. The system must have an air economizer. The heating shall be provided by a unitary package or split system heat pump that meets the heating table. The system shall meet the exhaust air energy recovery requirements of 6561. So now we've got exhaust air energy recoveries in these simple buildings. The system, because it is a prescriptive requirement, and it says we have to include all the prescriptive requirements, so this won't be, it'll be simpler, but it won't use more energy than a system built to meet all the requirements. Systems will be controlled by a manual changeover or dual thermostat. If a heat pump equipped with auxiliary electric heat is installed, then it shall be locked out only during the defrost cycle unless the outside temperature is less than 40 degrees. System control shall not permit reheat or any other form of simultaneous heating and cooling for humidity controls. System serving spaces other than hotel, motel guest rooms and others requiring continuous operators shall have, and which have a system greater than 15,000 BTUs, shall have a supply motor with 7.5 horsepower motor. More than 0.75 horsepower shall be provided with a time clock and have setback and have optimum starts. And except for piping within manufacturer's units, HVAC equipment and piping, insulation and painted canvas, that the piping has to be insulated. Ductwork and plenum shall be insulated in accordance with the tables. Construction documents shall require ducted systems to be air balanced in accordance with the tables. Outdoor air intakes shall meet the requirements. Where separate heating and cooling equipment serve the same temperature zone, thermostats shall be interlocked. Systems with a design supply capacity greater than 10,000 shall have the optimum start. Systems shall comply with the demand control ventilation requirements. The system complies with outdoor air switch requirements. And then we go all the way to S. So anyway, with S requirements of on a simplified approach, we do not believe it's simplified. So we have actually gone to the full committee 2 times and asked if we could do away with the simplified approach, because what happens is we have to rewrite the requirements into the simplified approach from anything we change in the main body of the standard, and so there could be problems and mistakes made there. We wish we didn't have to do it, but the main committee says it's wonderful to have a simplified approach. Everybody loves the idea of a simplified approach. We cannot do away with the simplified approach even if it's no longer simple. So it's in there, even though we have S extra requirements now, where we try to start out with just 2-3 requirements. So And that also served as a little review of some of the requirements in the standard, is why I bothered to read through it. Okay, Section 8, power. Now this leaves the mechanical section, but it's important for you to know about. This is the most unpopular requirement in the standard. This requirement is to turn off within 20 minutes after a space becomes unoccupied 50% of the outlets, or 25% of the outlets in modular furniture. You have to visually differentiate the plugs that are going to be turned off, and it's for for private offices, conference rooms, printings, copy rooms, break rooms, classrooms, and workstations with a 25%, well, 25% if they're not modular. Anyway, and everybody does not like this requirement. Now, people should like this requirement. The reason this requirement's in there is it saves energy. It is for after hours when nobody's in the room, so why would anybody complain about us doing something when nobody's supposed to be in the space? It saves energy, you know, should not be impacting people. Now, what we did was, and you can ask around, you can look at your own organization at night when with a building built to Appendix G standards, with the night setbacks and all the things we have in it, we would think that maybe 10% of the energy should be used when that building's unoccupied. No more than 20% for sure, you would think. But now we have all these 15-minute meters, and we can track how buildings operate throughout the 24-hour period. And buildings are running 50% and more of the energy when the building's unoccupied than when it's occupied. And we go to places all the time and ask this question, and we get the same answer. Yes, it looks like that our buildings are running this from Army bases, from people, from public, from normal industry buildings that hold multiple buildings. It's true. So this is what we were attacking. We were trying to get something in there that did not cause a problem and actually address some of the things that were happening at night. Now, but again, people say, well, everybody's going to the unswitched outlet, putting in a power strip and plugging in all their stuff in the power strip, so you're not doing anything but costing us money. And that's true, I guess, if that's what's happening. But again, if people would take the same attitude that we did to litter and stuff like that, and not just try to beat the code, but try to go along with what we're trying to do, this could save save some energy significant energy without causing any problems. But instead, we've actually had people tell us that their standard is to fit out a space and then put power outlets along the back wall equal to 50% and turn them on and off even though nobody's using them. So, you know, that they're just going out of their way to beat the code. But anyway, that's my soapbox on this deal. Also, let me think, there was one other thing I want to say about this, and it was good, it was interesting, but I can't think of it. All right. Electric energy monitoring. Now this is something that's new. That's new in 2013, and in 2016 we added the requirement to connect it to the DDC system. But this to me is a bigger impact than the outlets, because this changes the way you normally would wire a system for the electrician. Now the electrician is probably going to have to add a panel, and that's probably going to cost more money, but the wire management that he's going to get out of adding that panel, and what he pulls out, and what future people do, and what you would do as you came back to a building doing a site survey, is going to be tremendously helpful, because what we've asked for is for the HVAC systems, the lighting systems, the site lighting system, the plug loads, and the whole building all be monitored separately. So You'll have a meter for the HVAC, you'll have a meter for the lighting, you'll have a meter for the site lighting. And how you do that, how you collect that, will cause you to separate certain loads probably. Now you could go to each circuit and you could use an intelligent system to monitor each circuit, and each circuit would feed back to a total. But it's going to be probably more cost effective to monitor a panel at a time and to have everything in that panel basically be feeding one of these breakdowns. Now, we do allow 10% of the load in each panel to be from serving something else. So occasionally, you can have some other type of code there. All right, other equipment. Elevators. That's what I was going to say. One of the other reasons we went after plug load is because plug load is a big enemy to energy modeling and to meet lead requirements or anything else. Because if you're saying I'm saving this much energy, what you do is you say that the total energy of the building is divided in your savings between your baseline building and your new building or savings, and then you divide by usually the total energy used in the baseline building, and that includes plug loads, and plug loads includes all miscellaneous loads and all deregulated loads. So if plug loads are deregulated, then they run their that nighttime energy use is in that denominator, and no matter how much energy you're saving, if the denominator is big enough, it wipes out the percentage, and the percentage is what you're looking at. So that's why we include elevators and all these other things in regulated equipment, trying to lower this plug load or process load or whatever that's in the bottom. Now, in federal buildings, they take those out, but that's not the way the 90.1 or LEED says you're going to say what your energy savings are. They say you're going to use all the energy used in the building. Again, like the federal government says, no, we're going to take out the unregulated loads and just look at how much energy we saved on what we're regulating. Elevators are, we so far document or have requirements for the lighting in the elevator, for the ventilation in the elevator, and we require the elevator to go into standby mode if it's down, if it's waiting for longer than 15 minutes. We have the doors open and the lighting and ventilation de-energized. And new for 2016, we're going to have the architect list on the design documents the usage category from an ISO standard used in Europe. Hopefully these will be adopted in America quickly, or some, we'll pull out portions of this from ISO 2574642, and energy efficiency per ISO. You can see the tables, table 7. So what we're doing is we don't have any requirements for the efficiency of the actual lifting and lowering of people or freight in an elevator yet, but we want the public, we want the design professionals to be aware of these standards and to learn how to use them. And so that's all we're doing in 2016, is requiring them to be able to look up, use that ISO, use that table 7, and put that information on the documents. And in the near future, we'll start setting a minimum efficiency requirement for lift per foot or some metric like that. So we'll actually be trying to impact the efficiencies of the elevators. Escalators and moving walks. So as you walk up to this escalator, these sensors will sense you coming, and they'll turn on the elevators and bring them up to speed. And they'll slow down to the minimum allowed speed or off when there's no passengers nearby. Again, this is to save energy, and usually in off-hour situation. I happen to be lucky or unlucky enough to fly through Japan fairly often, and normally the plane I fly on is there just as the airport is going to open. few minutes before it opens. So as I walk through the elevator, I turn on the walkways, and the elevator and the escalators as I go through. It's kind of, you know, you're walking through this giant airport all by yourself, and as you go, all these things are turning on and off. It's kind of fun. All right, whole building energy monitoring. Now this is back to not the sub-meters, this is the real meters. So what we did was we've had a requirement for some time, and this is new requirement is I think 2013 requirement, but we had a requirement that you had to have a whole building electric meter, and it had to be a 15-minute meter, and we were monitoring the whole building electric use in a minute. Now the electric industry said that's not fair, you know. We have natural gas, we have fuel oil, we have propane, we have steam, we have chilled water and hot water that are also used as energy conduits into the building. And so to say we have to be metered is unfair. So you have to have a 15-minute meter on all the competitive type energy. So that's what we've done. And you know, some of it might seem like overkill, but most of these would have 15-minute meters on them anyway. Probably natural gas wouldn't, and most people know it goes into the boilers and stuff. But anyway, it is a requirement to have the 15-minute meters on all these requirements, with a few exceptions. All right, so that completes what we were doing today. We were running a few minutes early.
Mac, I've got 3 buildings and 6 slides that I can talk about. Building envelopes with daylighting and lighting, and we could do that for a little bit. This is right, starting in slide 281. You could just go to there. Don't need to.
He can give you the thing back. You're ready to go, aren't you?
I'm ready. Well, yeah.
All right.
Hang on, show my screen. Click.
So you're getting your money's worth today, guys.
So we try to do a few postscripts or appendices for your information. This is about 6 slides, 3 interesting buildings. We're shifting gears in a radical way. So we're talking about integrated design at the very earliest design stages and some of the strategies that you use relative to daylighting. Now, if you go back to what we talked about last week, with daylighting be a mandatory requirement in buildings starting in 2010, and in 2013 having 2 levels of daylight zones, primary area and a secondary daylight area. So what we're looking at is a few examples of buildings that use daylighting very effectively. So my rule of thumb, and it's been for some time now, 25 years at least, over a wide range of efficiency of lighting systems, that when you have lighting, electric lighting in a space, and you're applying daylighting to that electric lighting, the daylighting will effectively let you reduce the lighting energy in that space by 50%. That seems to be what I see, and it's been around for a while. So if that's the case, you then want to maximize the building's floor area that's using daylighting. Now, if you take a typical office building with a large footprint, you're typically getting only 40 to 50% of the floor area in daylighting. And what I'm showing you is a building in Sarasota, Florida that has an interesting shape and use of windows. Now, it's not a high-rise building, but it's a low-rise building. And what it's doing is it's virtually eliminating windows on the east and west facades, where it's difficult to effectively use daylighting in the early morning and in the late afternoon because of low sun angles. It maximizes lighting in the south, or windows in the south and in the north, and adds a roof monitor that captures light very high up and lets it reflect down into the space. So this small building effectively has 100% of its area that's daylit. And it's pretty uniform and pretty effective. So this is just an example of a small building that very effectively uses daylighting. It's the sort of thing that you want to have an integrated design of the lighting designer, the architect, and the HVAC engineer very, very early in the process to get as cost-effective a solution across the board as you can. The next building, and that's shown in from the outside, the photograph on the lower right. It's not in Sarasota, Florida. It's the National Department of Natural Resources office building in Wisconsin. And it's a very different climate, same design strategy. Eliminate windows on the east and west, have windows on the south that are shaded, and north-facing clerestory and north-facing glass that doesn't have direct beam sunlight. And you see at the upper right of this slide that you have a very pleasant interior space that doesn't have glare issues. It's actually not using a white ceiling, but it's using a wood ceiling that reflects light down, but it's very soft. It has high partitions for privacy, and yet because the partitions are not facing in toward the windows, you have virtually 100% of daylighting in this space. It's really a nice solution. The baseline on the upper left met the code in Wisconsin at the time. I'm not sure whether it was 2004, 2007, but it was, you saw your baseline at kBTU per square foot at 125, and the building as modeled was at 61.9 kBTU per square foot, and the building as metered was less at 53.3. And both the building as modeled and as metered were about half of what the code at the time was showing. So even if you have 33% savings from that point to 2016, you still have a daylit building. It's very pleasant, that's consuming considerably less. So these are two just example designs for small buildings. Now let's shift gears and look at a high-rise building in Manhattan, the New York Times building. That was a case study. This building used extensive pre-design analysis. You're seeing some pictures of the building as built, and this building uses a lot of glass, but it effectively uses some very good external shading strategies to minimize the solar gain on the window surfaces. You have horizontal bars below the desk height. You have an open area in this third picture on the right. When you're seated at your desk or walking around, you can see out the window, but above that, you have horizontal external shading that effectively is blocking the direct beam light on the windows and reducing the cooling load. You have very expensive low E double pane glass that is reducing the heat loss. And you have, and you can see it on the left here, you have automatic blinds that are controlled by the brightness of the window surface for which the blind is controlled, and we'll see shortly how that works. So in this example on the left here, there's no light on in this band. There's a slight bit of light on in the bands of light moving inward from the window surface. So this is a really interesting building. It had funding from the Department of Energy, funding from the New York State Energy Office, NYSERDA, and funding from the California Energy Commission. And it had extensive technical input from Lawrence Berkeley National Labs Windows and Daylighting Group. And here are the facade layers, the external layer with fixed layers of shading for light diffusion. You have low E spectrally selective, thermal control, solar gain control. There's frit on portions of the window for solar and glare control. And there's an internal layer of a dynamic motorized shade system. We'll see this shortly. And there are 4 facade layers on each floor going from floor to floor. Floor to desk, desk to head height, head to ceiling, and plenum. Very, very elegant design. And then a 5,000 square foot test facility was built before the design ever began to test 2 different types of shading, daylighting, employee feedback mock-ups. And they were concerned about glass with window glare, control for solar heat gain cooling, and daylight harvesting potential. And real sun and sky conditions were near the construction site, and it was done for a 12-month monitoring period prior to construction of this very large high-rise building. And then when the building was being constructed, there was a group that came in and did testing using an HDR camera pointed at the window surface and was measuring the luminance or the brightness of the window surface and the response of the automatic blinds and whether the blind control strategy was working. It's a very effective design, very technically rigorous. LBL has been involved with the city of New York trying to encourage other office buildings in Manhattan to use similar techniques. They've had mixed success, but it's a interesting strategy and set of buildings. But all of these examples, to be successful and to be cost effective, really needs to have involvement of the entire design team very early, even before people sit down at the computer monitors to do the early design. And then the design team needs to keep tracking to make sure that changes don't reduce the potential energy savings. An early daylighting solution that I was involved with in Minnesota was a test facility as part of a utility program. It was a 100,000 square foot addition to laboratory and office space. And it had a really good daylighting design that was finished as part of the building. And the utility was wondering whether the program should intervene in the construction process. And the decision of the utility team that I was consulting to said, no, let the construction process go as it normally would and see how well the daylighting system works without our intervention. So they tested the facility as construction was, of the lighting and daylighting system was finishing. And they determined that there were the wrong number of sensors in the wrong number of locations. The sensors were never calibrated like this photograph we're seeing. And the daylighting system didn't work at all, didn't save any energy at all. Since the utility was financing the incremental cost of the daylighting measures at that time, the utility said to the contractor and the owner, we're not going to pay for the subsidy of this unless this works and you go back and fix it. So the contractor went back and fixed the problems, and the daylighting did indeed save the 50% that they thought it would. So this is some interesting examples of design solutions that go way beyond simple compliance with code requirements, and sort of thing that if you're involved in doing whole building and energy analysis, either for utility programs or for LEED or other analysis beyond the standard, this is the sort of thing you can get into. Okay, that's the end I've got. So perhaps we go back up to our evaluation and certification. If you have questions, we want you to complete the course evaluation form, and you're going to do this online and submit it. If you have questions, talk to Kelly Arnold, karnold@ashrae.org. If you have questions about other ASHRAE courses, contact edu@ashrae.org. And just a comment, a third of our audience today is from Canada, and Mac and I will be doing in March 2 3-hour sessions, one involving a discussion of ASHRAE 90.1 2013, which is widely being adopted by many jurisdictions right now, and a 3-hour course on Appendix G, how you use Appendix G both to comply and go beyond the requirements of the standard, and that will be in the Toronto area. So you can go to ASHRAE Career Path for IAQ and energy savings practices. There's ASHRAE's energy certification program, and there are a number of credentials you can get through the certification program. All right, I think that's the end. Here's your evaluation certification. The access code is A2Q5. It does work. I used it myself earlier today and downloaded the PDF version of the course materials. And okay.
I do want to remind everyone that a recording, you will receive a link to the recording of today's presentation. It should be available in about 48 hours. You should have received the part 1 recording last week. So if you haven't had a chance to look at it, be sure to look at, when you look at the email from GoToWebinar, the same email you use to register for the course. So if you didn't receive it, please look in your spam folder, but it should be from the GoToWebinar, the email from GoToWebinar. So if you do want to receive a recording, and a recording of this presentation should be up for about 6 months using that same link.
A2Q5, okay.
Want to give them one more chance to ask a question?
Yep.
Again, you can always email us. I think both our emails were in on the end of the envelope presentation.
That is true. Okay.
All right. Well, thank you very much.
Yeah. Hope you benefited from the 2 days of presentation. Good luck with it.
Yeah,
See you soon. Okay.